known. I personally often make folks that work with me read Christoph's paper on what is it called? Forecast evaluation for data scientists, common pitfalls and best practices. If you haven't read it, you should read it. They have in common that both have had a change of job lately. Christoph is now with the University of Granada, and Slawek is a distinguished scientist at Walmart. Commonalities continue. You know, when you write something, I typically read, and when you talk, I listen. So this is the moment to do this now. Please welcome our speakers.
Great, thanks very much. Yeah, great introduction. So we got a mic, so I hope you can all hear me well. It's not too loud. Yeah, so our talk is called Probabilistic and Summary Forecasting. But the thing is, I thought I also want to talk about these pitfalls and forecasting practice. So that actually we have kind of three parts. And my part is this first part where I actually talk mostly about that paper that Tim just mentioned. And then I will transition a bit into the probabilistic forecasting and then hand over to Slawek. Then he continues with the probabilistic forecasting and the summary forecasting. So yeah, motivation, exactly that. We wrote recently this paper. I also have a paper forthcoming in the Foresight Practitioner journal, which is just a kind of shorter version, so then Tim can make his people read the shorter version. They don't have to read the 40 pages. That's what people mostly complain about. It's 45 pages, he's going to read that. But yeah, so the main claim in that paper is actually that many machine learning academics, they don't really know how to properly evaluate forecasts, right? And like I'm seeing that continuously when I review papers, also when I read published papers. And I just thought, why should I be the only one getting angry? Like I can just write it all up and then people can get angry with me. So more fun for everyone, right? And I think that even becomes more relevant now because we now have this kind of generic data scientist job title where very often like a data scientist has to do many different projects, but then they also do a bit of forecasting and they have this general ML stats background and then they get into forecasting and yeah, sometimes don't really know what they're doing or how to evaluate and so on. And so I think in the paper we didn't structure it that way, but then when I thought about it, there are actually kind of 6 main kind of problems that I see and where I think people really need to look out for, and here they are. So the first one, too small data sets or irrelevant data sets. Now, I think as a practitioner that's not so much of a problem, but it's more like if you read a paper, then just kind of look out for that. Number 2 would be the data leakage. Number 3, not using the adequate benchmarks. 4, wrongly used or ad hoc evaluation measures. And I think number 1 to 4, they are quite straightforward what they mean, but then 5, reliance on forecasting plots for other things and sanity checking. And 6, assumptions that a forecast needs to be a realistic scenario. So they are a bit more kind of not so clear what they mean, but I go through all of them and we'll have a look. So the first one, data sets too small or irrelevant. So actually this one is a quote. Like if a method has more words in its name than it has time series, it is tested on, then be skeptical. That's actually Stefan, who is here as well, pointed me to this one, and he adapted it a bit, so I actually credit him for this quote. But it's adapted from Goodwin 2011. So if in a paper you read something like, we have tested our method on 3 stock market time series, then I'm like, well, if I go on Yahoo Finance, I can download 500 series easily. So why did you use these 3? Why not other 3? And, why care about those? So, like, if clearly they could have had more series if they wanted to. And they don't really explain, like, why these series, or nothing in their methodology is kind of particular about these series. And you kind of get the feeling they don't really care about their methodology. It just happened to their method just happened to work on these series, right? So, I'm always quite, critical of these things. Problem number 2, data leakage. It's surprisingly difficult to avoid data leakage in forecasting. And probably most of you or all of us have had this experience. So, and the problem is obviously the rolling origin setup, where basically data travels from the test to the training set. So you train, you test on the data, and now time has passed, so you shift that data into your training set and you retrain. And what that makes is that it's quite difficult to really separate your training code from your evaluation code. And when I say difficult, it means that at least it can be computationally expensive, because usually you have your training set as a matrix, so you run everything on that whole matrix. So now you need to run on like each row in that matrix separately. So it's a bit kind of cumbersome. So people don't do it. People use just the same code base, and now you basically need to trust whoever implemented the thing that there is no data leakage. Yeah, and so in machine learning, you would usually say, well, don't normalize your whole data and then afterwards separate into training and test, right? Because there's obviously data leakage there. But in forecasting, there are so many more opportunities for data leakage. So obviously there's normalization, but any form of smoothing or decomposition that you do with your data, like if you do STL decomposition and then afterwards you separate these components into training and test set, that's obviously not good. And for some reason, there's this thing called empirical mode decomposition, and for some reason there are a lot of papers that use this that do exactly this wrong. So basically when I read a paper about empirical mode decomposition, the first thing I check is, do they do any form of windowing? Because if they don't, they usually just run the EMD over the whole series. And then what EMD does is it extracts some very low frequent components, and they obviously contain information from everywhere in the series. So you would just know that in your test set it's going to be a trend, right? And then they get these incredibly good results. And obviously it's not usable in the real world. And another interesting point I wanted to make is that I think like if you run a global model on, let's say, M3, M4 data sets, you have problems of data leakage. It's much more subtle, but basically M3 and M4, because they are not aligned, you have some series from the future and some series from the past. And now if you think of something like COVID or the Ukraine war, like these big global events that affect everything, you could now think that some series probably have these effects in them and others don't. So that global models I would argue that on M3 and 4 data set, global models have some sort of unfair advantage over univariate models. We all know global models also work great on things like M5 and so on, so it's not a general criticism for global models, but I think we need to be a bit careful here. Okay, problem number 3, not using adequate benchmarks. So, well, we all know it, always use simple benchmarks, right? Especially when you have like high noise series such as assets, stock prices. And one quite interesting discovery we made in the paper is that there is this pocket of research in machine learning where people come up with all of these transformer architectures, and well, they have informer, autoformer, ROB former, ETS former, who knows what former. And well, just to be clear, so I'm not saying transformers don't work. I don't have really a strong opinion on that, but what many of these papers do is they use a data set that was introduced in 2018 in a paper by Lai et al., where they use an exchange rate data set. And now they say, okay, we have this exchange rate, it's like 8 exchange rates, and we predict that 720 days out into the future. So about 2 years exchange rate forecasting, purely univariate, right? And now each of the, well, Informer doesn't use it, but the other ones do, and each of them beats everyone else, right? Like each of them beats like whichever papers were before. And I thought, well, that sounds a very daunting task to do this prediction. So And none of them uses naive forecasts. So we just use the naive, and they all lose against naive. So, and another interesting thing is that then sometimes they find kind of, weekly seasonalities of 7 days out and things like that. But that data set has only training days. So a week is 5 days long in this data set. But they don't know. So anyway, it's not a general criticism in the sense that they also use other data sets where I think it's a lot more credible. But whenever I see this exchange rate data set in a paper, I start to, look more carefully. Okay. Problem number 4, wrongly used or ad hoc evaluation measures. So, if you think about it, evaluation, the easiest things you can do, RMSE, MAE, and they work well, but now if you have series on very different scales, then obviously the series with very high numbers will dominate your evaluation, so you want to somehow make it scale-free, right? So for that, usually you need to divide by something, and the problem is that after 30 years of research in forecasting, or more, 40 years, we still are not really sure by what we should divide by, in a way that it works always under any possible non-stationarity, any possible series characteristics. Like, there are over 40 error measures in the literature. We all know, S-mate, Maze, but they are, we found 40 measures around, they're all in the paper. And for every single of these measures, you can think of series where the measure does something that is weird, right? So, and I think then, if you have a general ML background and you don't really know that, then just don't invent your own measure and say, it can't be so difficult. It really depends on the characteristics of your data, which measure will be adequate, right? So if your series are all these typical, let's say if you have solar power production, of course you can just divide by the mean over the series. But if you have something like, series that grow a lot, like Bitcoin price, the mean of the series doesn't tell you anything, so why would you divide by that? Okay, number 5. So these 4 were the kind of quite straightforward ones. Now number 5 and 6. Number 5, reliance on forecast plots for other things and sanity checking. So what I mean by that is that fixed and rolling origin evaluation are obviously very different, right? So what you see here in this example is a naive forecast in blue fixed origin, and in red just one step ahead rolling origin naive forecast. Well, and what we see is it does what a naive forecast does. It just follows the series very quick, it just follows the series. And one problem that I always have with these plots is that kind of, the distance kind of horizontally is very small, but obviously the distance vertically can be really big, and that's what your error is calculated over, right? And now often you see plots like these in papers, and you are like, okay, so we have a couple of different methods. They all follow the series, but how am I supposed to now from this plot know which method is better than which, right? It's like, what is this plot really telling me? I don't get anything from this plot, because if anything now I would have to say, so it seems that here, so the green one, that is the neural network, it seems that it's here a bit worse than the others, here maybe a bit better, I'm not sure. So you kind of need to now in your head do the same analysis that the error measure would do, to kind of just try to look at all the vertical differences and then somehow average them in your head. So for me it's like, if you do rolling origin one step ahead, then plots are really only for sanity checking, to know that your method doesn't do any super crazy, but to determine which method is better than the other. I don't think that works terribly well. Okay, and the last one, assumption that a forecast needs to be realistic. So what do I mean with that? So if we look at this one, which, I say it's a share price, but it's not. It's just a random walk. So it's really just white noise cumulative sum over it. So here we know, obviously, if we do like fixed origin forecasting, that the naive forecast is the best forecast, right? Well, depending on the error measure, but yeah. Okay, so now imagine you have this forecast, you go to your boss, your manager, your stakeholder, and you say, this is my forecast. And then they will probably say, well, but like, what happened to this trend? Like, is that not going to continue? And like, we all know that it's not just going to be magically like this straight line, right? Obviously, there's going to be something. So I mean, will the share price just remain constant in the future? Obviously not, right? But still, this is the best forecast that we can get. And I think the problem here is that, so if we just take one step back and we ask us what is a point forecast, so I have this quote that, well, all forecasts are wrong, but some are useful. That's like Tim and Jan, I think, have this on their slides, which is obviously an adaptation from George Box. So I think the idea is that the future always holds some uncertainty and some noise, and we don't know what will happen. So, and best is obviously to reflect this with a probabilistic forecast, right? And now if we do a point forecast, then that is obviously just some sort of a summary statistics of this probabilistic forecast distribution, and that could be a mean, a median, or mode. So basically, if you say, I want my point forecast to be the most likely future value, that is not the mean, that is the mode, because the mean, it's not the most likely future value, but the expectation. So it's actually kind of a blend of possible futures by their probability, right? So the expectation of if you roll a dice, the expectation is 3.5, but you never get a 3.5. You get a 3 or 4, yeah. So it's really like a blend of different scenarios. And I mean, for example, if you have intermittent series, then the most likely future value will be a 0, but that is not the forecast you want, right? So in that sense, I think we need to be really wary here that what we do with forecasting is really getting some summary statistics over the forecast distribution, and that can look like something that will never happen in real life. Okay, so with that, I would argue that to really understand what we do when we do point forecasting, we need to understand probabilistic forecasting. I think also Tim and Stefan, for example, have argued in that way we should always do probabilistic forecasting. Okay, so let's look at probabilistic forecasting next. So I mean, there are many ways to do probabilistic forecasting. So we could do analytical prediction intervals, we could do bootstrapping, Bayesian models, forecast parameters of a distribution, we can do quantile regression, we can determine we can determine the intervals empirically through backtesting or some new approaches like this level set approach. But actually, what we want to focus here now for the next part of the talk is the quantile regression. So maybe quickly to recap. So, I mean, I think, well, there are so many talks here in the conference about quantile regression. So, for example, 2017, when et al., they do that with a neural network. It's good, you don't need to do any distribution assumptions. So it's good if you have a lot of data. It's quite fast to compute, easy to implement. The drawback is you can get only certain quantiles. In practice, that's not necessarily a problem. You can have 5 to 7 quantiles enough. You can also do this interpolation between the quantiles. And an interesting thing is you can also fit different quantiles at the same time. So with a neural network, you can do that quite well. When you just have losses for each quantile and you combine them into one loss function. And you can even do more interesting things, which is actually now what Slawek is going to talk about. So, handing over to you. Yeah. Just put it here. Yeah. It's better.
No. And then better. Happy to see you. Okay, I hope now.
He just mentioned it.
Because I think
He did just mention but you can also do any radio
without that.
Maybe just start and
So I will switch it up itself.
I don't know if I'll be able to fix it or not.
Get some
There's a microphone. It's
Awesome.
check. Okay.
One of them is just the message.
yeah, exactly.
I came up with the wrong moment.
So the mic was actually for him. Maybe if you just stand there.
Yeah. Oh, okay. Yeah. Okay, thank you. So we can, neural network can be trained to forecast any quantiles, and number of quantiles at the same time. The question comes, what quantiles, and Christoph says that we can have such bunch of them and interpolate, but there are some problems. First of all, successful forecast will be used by many different departments, and some of them will care only about P90, some will care about 50, and these high quantiles. So the list of quantiles will grow, and the high quantiles, which usually are of interest, like 97 to 1, they may not be easy to interpolate because they change a lot. The difference between 50 and 51 is smaller than 98, 99. So then you would need to say, okay, maybe I interpolate. I have grid of every 1%, but maybe at the edge is still more than 1. And then you produce, 120 of them, and then it turns out that you actually use 2. So it is wasteful. Also, in some business context, it's actually nice to have dynamic situation where just imagine you have some forecast and you have some slider, and you can go from 50 to 98, 99. So graph would dynamically adjust and display quantile a user wants. So business users love it. So that would call for possibility of of predicting particular quantile at runtime, at inference time. So ideally, we would like to train a system to predict any quantile requested, but requested during server inference. And that's very much doable. The idea came from this paper with Adele Good and Kashi Russell, this probabilistic time series forecasting with implicit quantum networks. What follows is modified, I think simplified version of it. Oh shit. Alright. So, for machine learning system, I mean, sort of a reminder for those of you who don't have daily contact with that things. Really, there are two distinct phases of using machine learning system. There is training and search. In training, neural network or generally any machine learning program, you train weights, you set up weights, adjust weights, or some machine learning parameters. At the end, we save them. Then we have separate serving or inference program, which loads the stuff into memory, and then serve. So weights for inputs can be list of series or quantiles. The forecasting is very quick because no optimization takes place, and for large batches, especially, we are talking like milliseconds per time series. So it's much faster than traditional algorithms. AIM exponential smoothing will much slower for large amount of time series than trained system. Training can take long, yes, and maybe days, maybe weeks. I think this machine, this large language models, they are training for months on monster amount of hardware. But the inference is faster. Right? They respond very quickly. So that's the primary difference. So normally how is the training with neural networks? So we have, we create batch, in this case 2 time series in a batch. And then we have a kind of sliding thing with input window, output window. We extract features from input window, and then we will be stepping through and comparing output of neural network in output window to reality, calculating loss after number of steps, averaging loss, updating. Maybe several times during steps, a single time at the end of batch. So this is very much standard thing to do neural network, especially recurrent neural network. The step in time is necessary in sequence. What can be done, however, is that at the moment of creation of batch, we randomly sample quantiles. So, for example, we assign this 021 and 0021 to first time series and another one to second one. And then what you see here is kind of simplest, decently performing recurrent neural network composed of 2 cells. So you have this, time step 1, time step 2, time step 3. The input comes. We are appending this quantile, and for good measure, also appending that thing again for every layer, input to every layer. So input comes through this thing and then ends up in Y1, and then next time step goes Y2. Linear array is needed because the output size of these guys tend to be something like 100 related to complexity models, whereas what we really need is what the forecast is about. If forecast is 13 steps ahead, then these vectors y1, y2 needs to be 30 steps long. So now we are creating matrix, basically linear matrix, which converts this 100 output into 13. So loss function is a quantile, but quantile loss for this particular one. So we'll be judging how neural network perform it, outputting for this requested quantile. And that's pretty much it. The whole thing works. The minor amount of sophistication is we don't need to sample from uniform distribution, because people usually have interest in edges. I mean, usually high, but potentially low. So you can sample, and that thing changes here more quickly, right? And we want to be more precise here. So we can sample from something like beta 0303, oversample here, model pays particular attention, but if it's symmetric, it's okay. It will still be good here in the center. And then comes serving, right? So we train a model, comes serving. So we get a request for time series, this particular time series, and we say, let's do 2 quantiles. So it can be more complicated, batch can be bigger, multiply time series, but let's say multiple time series, but let's say, single time series just repeated with 2 quantiles. And the same, we just append in these quantiles and we get output. What is interesting, and it was really interesting, that the accuracy of center forecast, quantile 0.5, can be as good as a similar architecture, dedicated system doing only point forecast. And I know that sounds a bit, but a few years ago this idea of multitask learning was very fashionable, and I understand it can be skeptical, but I've seen it myself. Occasionally, at least, multitask learning works. So if you train it to do more, to train the whole distribution, you don't lose on the quality of center forecast. Not necessarily. And if you lose very little, and occasionally it's better. I really saw that thing performing better. All right, so summarizing this, any quantile idea, because it's really idea, it's meta-algorithm. I show you recurrent neural network, but can be implemented in any neural network architecture. And very likely other machine learning models. So we generate quantiles randomly during training, apply proper loss for this quantile, and during serving we provide quantile, and it works very fast, milliseconds per time series. So it's very large batches that really can be very fast. All right, so now I'm moving to a different topic, which is summary forecasts. So normally we are forecasting some value which is result of direct measurement. So it can be, every 5 minutes we measure temperature. But then maybe we don't care about temperature every 5 minutes measured, we care about daily average. Or maybe we care about minimum, maximum bunch of quantiles. So we can actually forecast this statistical summaries. Instead of doing distribution, we can directly go for summaries. And idea of forecasting summaries, I will concentrate on quantiles. I think it's unusual. I mean, I'm not academic, I didn't read every paper in forecasting, but I've never read about something like that. But I believe it's the right choice for situation where data is in high frequency, but you make decision in low frequency domain, and that's pretty common in business, getting more and more common. So just consider that we are asked to do 12 months ahead forecast hourly grain, right? And that will be 8,000 points. So that's not rather challenging stuff to do. And if miraculously we manage to do it, users would aggregate it anyway. So if you provide them hourly for the next 1 year, and you bring it to some capacity planner, they actually will ignore everything. They will look, what is my P99 maximum in a quarter? Right? Because that's what they plan capacity. They don't care whether the maximum will be 23rd of December at 17 or 23rd of November at 11 a.m. It doesn't matter. The point is, what will capacity I need in 9 months' time or 1 year time? And therefore, even if after heroic battle you provide them with high frequency forecasts, they will themselves aggregate it, or they will request you to aggregate them. Like, give me a table, not quarterly summaries or something. So even if they tell you we need hourly forecast for 2 years, no, they don't. Most likely they don't need. They think they need, but actually they don't. And we can provide what they need by going directly to quantiles. And quantiles have good business meaning because quantiles can be cast as a balance between cost and risk, right? If you tell them, if my 95% forecast is perfect, 5% of time the reality will be above my forecast. So do you, big vice president, are you happy with 5% of our system not able to slow to respond to our customers? If you are, great, right? But otherwise, this is his business, right? So the point is, you can cast it as cost against risk, right? We need double our capacity, then fine, then we will be 99.99, whatever. So quantals really have good business meaning. So what you see here, I hope you can see. So this is what I've done here. So it's 12 months, January to December. On axis are percentiles from 0 to 100, and note including minimax. So dots are forecasts. Blue line is what really happened. And this is like 7 points multiplied by 12 months. That's the whole forecast. And that provides users what they really need. Additional benefit of doing this sort of things is that about input preprocessing was robust. When we have high frequency data, the more high frequency data is, the more likely it is that we have missing values, right? And the missing values tend to be failure of data collection, misconfiguration, failure of hardware, programming error. So these losses are unrelated to the data, and therefore we can lose quite a lot of data, but quantals will be similar. If you think. So missing values is generally a problem, right? For tree-based algorithm, it's a much smaller problem because you can, for counts, you can put -1, and that's sort of good value saying this is missing value. But for neural network, it's much more troubling. And sometimes it's easy to do, usually not. Imputation may be complicated. Maybe you need to create some shadow vector which says, yes, or missing 0, so 1110 something. It's less elegant than in tree-based algorithms. And anyway, imputation, so may not be always easy because some obvious imputation may be a legitimate value. 0 is legitimate value for counts, right, for purchases or something. But they're not impured. And just kind of, let's say, rule of, if I want to forecast 6 months ahead, so you see hourly data, 6 months, and this monthly chunks, right? So in each of them we calculate a bunch of quantiles. Here is 150, 99. So this is, let's say this is 6 months input. We want to, rule of thumb is you want to predict something. In machine learning, your input should sort of resemble the output. So if you want to predict 6 months ahead, a bunch of quantiles, input could be for 6 months of similar quantiles. And we can lose when we go to even, and these quantiles will not move much. We can lose a lot of data, and quantiles will stay. And we don't need to do any imputation. It's fine. I added also the 17, just to remind myself and you that while we can predict number of quantiles, right, 199, whatever, but we can also merge this idea with the previous idea of any quantile. So we can generate quantile during runtime, 17, pre-process data in memory for this 17 guy, and then forecast next few months of 17th percentile. Right. So this also can be done. Not the number of quantiles, but with a training system to do it any quantile forecasting. also note this quantiles. This is input, but if you think about output and loss function, it won't be pinball loss. We will be using central metric. So each of these guys we will put in some sort of central metric. And we absolutely can have min-max. With pinball loss, it's struggling to have. How do you do, min-max using pinball loss? But here you can, because you just put central metric, it's just some sort of difference or percentage difference. So we can do that. And then hierarchical reconciliation. So if we have this low frequency quantiles based on high frequency underlying data, of course you may come to a situation where you need to reconcile it, because you can have a bunch of routers and one bigger one on top or something like that. So last year I presented my joint work with Alalay from Meta, Rasenjo from Meta, and we presented two methods of reconciliation. One was based on extending summation matrix, where sum is not equal 1, it's not supposed to be 1, sum is not equal number of components of bottoms. And then following various approaches of optimal reconciliation family. Another one was minimization adjustment. So there are some historical relationship between these components. So we are doing, let's say, P25, right? And we have 10 components. So they tend to be reasonably stable relationship between these 25 percentiles of components and 25% of top. So we can try to minimize adjustment of forecast needed to get this historical relationship preserved. So it can be done. We've done it. All right. So summarizing summary forecast. When the underlying data is high frequency, and it happens more and more because storage is cheaper, right? So people are able to keep it longer and high frequency data. So when you do have high frequency data, and the horizon is long, the decision, actually, sorry, I forgot to say a little bit more, and I still have time, so I should have told it 2 slides ago, but so I was talking to you about hourly forecast, 8,000 points, but now think about internet websites, and nowadays every company has internet website and they are transactional, right? So if user clicks on something and that thing doesn't respond within 30 seconds, they will lose interest, go away, or they will refresh. So to really measure the system is not underloaded, you don't need hourly, you need every 15 seconds counters. And I've seen that happening. People do collect counters in data centers, 50-second intervals. Now, if you have underlying data 50 seconds interval, that's actually good because it tells you whether there was some, 30 seconds or 45 seconds overloading. But I think you agree with me that, doing 2 million points forecast in France, that's not exactly a good idea. So, I calculated it's 2.2 million for 1 year. So this high frequency data happens more and is available and is useful because we do want to see what happens in this very short time scale. So it's good to have it and it's good to make decision, but decision should be based on this summaries and not on raw forecast because it's basically impossible. Learning is faster, a lot of technical problem disappears, and at the end users get what they really need. They really need summaries. And neural network can be trained and predict any requested quantile and serving inference time with high speed. So that's all. Thank you very much.
To the speakers, we have time for questions. I see the first one.
Okay, thank you. Slawek, wonderful talk, both of you actually. The part about training any ML method with general quantiles, you then enforce monotonicity so you don't get quantile crossing?
Well, so there are neural network architecture which guarantee that, but I would just sort them.
Yeah, well, sort them. Yes, of course you could do that, but in that particular use case where the user specifies, I want to have something on the 90th quantile, and then next he says, okay, that's a nice number, give me the 95th quantile, and suddenly,
So
whoops, what comes out is smaller than the 90th quantile, and he's going to be surprised, and then you can't sort it afterwards.
Well, I have an idea. I mean, in vision was they're using some slider, and
Yeah,
they
but-
probably will not notice.
Okay, but then first evaluate on all quantiles and sort them, and then provide it to the customer, right? So it's not
So
really
if there is a
question.
requested 20 of them, I surely will sort them first.
Yeah, because the way you presented it was really more of the user tells you the quantile value and then you serve up the results. But yeah, okay. But you can always enforce something. Okay, thank you.
There's another question here, Olivier.
I had the exact same question, see. So, but maybe your monotonic layer can actually solve this issue.
That will solve the issue. The implicit quantile function also? Will that solve quantile
So
function?
I talked to Adele, and she was giving me very sophisticated explanation why it's very unlikely. And I was telling her, okay, but eventually we sort.
Yeah, because sorry, in the original paper, I think they just sample in the end for 100 or 200 quantiles, and then they sort them.
Yeah.
But then that kind of sort of
But
negates
she was
the-
saying it's unlikely. She was assuring me that sorting is almost unnecessary, but just in case.
Sorry, that was, yeah. Ruben?
Maybe a question. So, how do you convince your users that your quantiles are good? So, I'm just saying, like for point forecast, we use maybe a MAPE or something, and okay, for quantiles we have like a pinball loss, but I often find that it's
So
it doesn't have like the same advantage as a MAPE to
No.
as for the interpretation, you know.
I agree. So for quantiles, for me the primary metric would be what I call exceedances, right? So for 95th, how often actual is above, or for 5, how actual is below, right? So we want in both cases 5% of time roughly. So my forecast, if it's properly calibrated, then roughly we'll keep these exceedances. So I was right last quarter, and actually that is my defensive weapon. If someone comes to me, oh, there was something going up, your forecast was too low, I say, well, that was 95. It's expected to be 5% above. Right? So,
But then
if it's not, that's no good. No, it needs to be exceeded 5% of the
But
time.
if I set my quantile 5% of the times to like 1 million or something, and then like 95% of the times I set it to 0, I also have like this 95% level, you see. So I don't see
I don't understand.
how that measure works.
So your 95th say it's 12,000, right, or something, and then we have reality. So that's for forecast for quarter or something, and then reality is doing like that, and then you calculate how often was above my forecast 12,000 content, and if it's not dramatically different from phase 5%, you are happy. So these exceedances, I think they are good intuitive measures for, of course, CRPS and so on, but this exceedances, how often it exceeded.
Yeah, but perhaps I can say something to that, because that's exactly what's discussed in the paper Spagniting et al. About proper scoring rules, about exactly this kind of strawman forecaster that will, in 5% of cases, give you a huge forecast, a very small forecast, and 95% of cases a huge forecast, or whatever the other way around. So it's a question of calibration and sharpness, really. And the pinball loss will penalize something like that. Or a proper scoring rule, if you're down at the probabilistic level, will penalize you for that and will incentivize you to be a bit more honest with what you're doing there. So I think that's probably going to be your answer.
And maybe I misunderstood what you're saying. So maybe you were telling we were worried that occasionally it goes to the moon, right? So it exceeds this 5% of time, but crazily much. But then we don't do one quantity, right? We get 95, 97.5, 99, 99. And then each stage you can say what percentage time I exceeded. So you can get.
We have, just a reminder, we have two speakers. So I will ask an embarrassing question to Christoph. Also, but there's a question to first.
Yeah, I wanted to ask Christoph. This frustration with people doing things in a way like not the traditional way, wrong way, right? The thing is, like, I feel like this is a classic example of all these silos. This set of people don't talk to this set of people, or there's very minimal transfer. But isn't it also the case, like, okay, they start off in a different way and they gain momentum, and ultimately they become like a separate field, and we've seen this. So from that point of view, isn't it in a way, shouldn't this community here, shouldn't they take more active more active control, and then try to go and maybe make collaborations with those people and get them onto this? I don't know. What are your thoughts? What can you do?
Well, I mean, I think so the machine learning community has a bit this tradition of disrupting other fields, right, and not kind of caring about what other fields do. So, so for them, they often don't feel the need to look elsewhere. But then, on the other hand, I mean, I think, that's a lot of the work that I do, right? This paper is published in a machine learning outlet, and so a lot of what I do is trying to go to the machine learning community. For example, Tim is also very kind of active in the machine learning community. So I think, definitely we have to do some work there. But then, on the other hand, machine learning, it's a field that moves very, very fast. And there are all of these new papers coming out, and they get really high citation numbers as well. And then sometimes, very quickly, there come, in short successions, 7 papers come out. They all use the same framework from the first one. Then somebody writes a review about these 7 papers, and there is your new research field. I see that happening.
Just for both of you guys, for your comments. How do you guys conceptualize sort of the spectrum of this scale, where of course you have to use some sort of machine learning because there's so much stuff, versus say if you knew the true data generating process and a Bayesian, full Bayesian sort of sense, right? Is this all just a necessary evil? Or what are your thoughts?
Well, I can say, this thing, true data generating process, always rings a bell, right? So, on the slides I had this, all forecasts are wrong, but some are useful. So that would mean there isn't any data generating process that we can identify, I guess. But then, I think you want to make a model only as complex as it needs to be, right? So that's where this idea comes from, start with the simple benchmarks, then build complexity in, and if it adds something, then that's great, and if it doesn't, then just don't do it. Right, so I think that would be.
So are you saying that the deep learning problem, stuff like that, is it necessary, or is it's just solving problems because you have them?
Well, it really depends on your forecasting problem, right?
Also, I know nothing about forecasting. I'm just trying to see how you guys think.
Yeah, so maybe let's put it that way. Another problem that I see very often also in this literature that I talked about is that they say we have this new method for forecasting, right? But then time series, there are so many different characteristics. A series can have thousands of data points, and I always think about if you are in energy forecasting and you're used to solar energy production and load, a solar energy production, that will be always between 0 and whatever is the max of what the solar farm produces. And then the value goes between those. So, and then there are these seasonalities, and that's a totally different time series from a series that has just these, exponential growth, and then it was down here, and now it's up there. So series can be so different, and then also the tools you need to use are so different. And I think that's also one thing that in the machine learning literature, they often don't have so much appreciation. They always try to have one algorithm that kind of solves everything.
I'll bet a bottle of wine that next year at ISF there will be a talk on foundational time series models that will solve exactly that question, but whoever wants to take the bet. But there was a question here.
Yeah, this is not a question, just to get a comment. So what if we really have to deal with short time series? Because I work with ecological data, so we do not have plenty of data at all. Because, for example, if we need to forecast the count of species, we usually go to the desert or go to that field manually to collect data. And there are a lot of missing values. So normally what we do is we aggregate per year. So even though we are collecting data from 1990, we just have only 23 data points. Still, we have to work with that. So just need a comment from you. In that case, what are we to do?
So I think, one question would be how many series do you have? So I would be more interested not so much only in how many points each series has, but how many data points you have overall. But then, just look at something like the yearly M3, right? And I'm not sure if there's any deep learning methods that win on yearly M3 or something. Still CETA could be the state of the art there, or LGT. So yeah, probably simpler methods will work better.
Mm-hmm.
Especially if it's spatial, if it's ecological data, you might be able to do some spatial modeling.
Yes, yeah.
If you have data points that are close together and then multiple time series, then you can do a spatial stuff.
Yeah, okay. Right. Thanks.
So I wanted to ask a question also. So some of the pitfalls I'm guilty of as well. So, taking the mean over the entire time series, I've done that before. It was painful. And working with the electricity data set, for example, where, a seasonal naive is impossible to beat. What's which of the pitfalls are you guilty of? The two of you.
So definitely data leakage. It does happen. If you are not very careful, it just happens.
It happened to me a few times, and as recently as 2 months ago, noticed by my boss. So it does happen.
Yes, are you?
When you showed the plot where you took the quantiles for 6 months, and then the idea was as a pre-processing step, and then you were going to use that to forecast just the quantiles. How do you decide how to break up that data? Like you broke it up into 6. You passed it. It was later on.
I think one more.
Yeah, that plot. Yeah, how did you decide to break that into just 6 monthly chunks instead of just one chunk, or weekly chunks? How do you make that decision?
It's partly what people need, right? So if someone tells me I need 2 years ahead forecast, I immediately think they probably don't need any more than quarterly, 8 quarters, probably. And if it's yearly, then 12 probably is plenty. So it's about context, what they really need. In this case, I thought 6 months. 6 months ahead sounds like 6 monthly chunks are good. It's not crucial. It could be 2 months. It could be 2 quarters. It's just.
We have time for one last question.
It's not a question, but mainly appreciation for what you mentioned, and just anecdote that the feature extraction could be very, very tricky. That can lead to the data leakage. Just one example of that when people are dealing with extracting, for example, promotions from sales data, and you don't have sales happening, you have to impute what was a promotion during that period. You may keep something constant, you may come up with 0, and that can lead to models to estimate that there was no sale happening. So we should forecast 0. And actually, I noticed that almost everyone that was using some sort of imputation to what type of promotion was happening during their backtesting, they were doing awesome. because their imputation has a signature that is either constant or zero or something that is easily detectable by model, and it's doing great because can predict zero sales exactly correct. And whenever it's dealing with actual data, then you will see the difference.
Yeah, these things are tricky to avoid, like this data leakage. It's really maybe one of the most.
Imputation is to be avoided.
That's actually one of my pitfalls, is just to not evaluate on imputed data. Yeah, that's maybe number 7. Or
yeah, good point.
All right, we're at time. That was a wonderful talk. Thank you all.
Pitfalls, yeah. Very good. Yes. Excellent. Oh, yeah. I had sequence.
And that's the main.
Writing a small follow-up to it actually is the like normalization methods. Yeah, global forecasting. I like about like when you do global modeling, but I guess that's not true universally. Like there are depending on the forecast accuracy on the small series could matter as much as the numbers.